then, welcome back to the course on robot mapping. So far we looked into Kalman filter-based approaches in the beginning of the course, and then also looked into particle filter-based approaches. And today we will start with a new topic and with a new kind of framework. And this is one of the most popular frameworks that we find today in the context of the simultaneous localization and mapping problem. It's actually known since quite a while, but only became popular over the last, let's say, 5-6 years. It was available beforehand, but mathematical tools which were available were often too slow in order to use it for real-world problems. But this has changed, and today we have pretty efficient systems available that we can use in order to address this problem. And what I'm looking into today is kind of least squares technique. This is kind of the basic methodology. So error minimization, least square error minimization, or least square, so squared error minimization. And the goal is to find configurations that minimize some error functions that So you can actually, you know this figure already, we can group that. We have the color filter we did, we have the particle filter we did, and we have these so-called graph-based approaches. And these graph-based approaches will be introduced today, and this is kind of the last big building block of estimation techniques we look into here in the context of the SLAM problem. And we'll look at different variants of this, but it's kind of the last big building block for that course. So graph-based SLAM, and in most cases, or in most ways, the graph-based SLAM problem is it's a least squared approach to SLAM. So we try to minimize an error. Typically, this is the error between what we expect to measure and what we measure. Very similar to what we did in the Kalman filter and other techniques where we try to find or recursively estimate our the state of our system given new observations, given new controls, and we try to find those states which minimize or which are best explained in the probabilistic sense, and we can actually show later on that this is strongly related to minimizing the error or the mismatch between what I measure and what I expect. So today we will not look into SLAM. This here is now a very general introduction to least squares. Because least squares is a very, very common technique. It's available since a few hundred years, and it's used in basically every discipline. I can't really say every discipline, but every engineering or science-related discipline, from biology to physics to any engineering disciplines, at some point in time, people are faced with error minimization, and this is kind of one of those standard approaches to it. So the idea is to compute a solution for a problem that is overdetermined. That means we have more equations than unknowns. So we have some information that we want to use to solve an equation or a system of equations, but typically we have more equations than unknowns. So more information than the unknown variables one has. What problem do we typically have in real-world situations when we are faced with such a problem? So what happens if you consider a few years back, you had a system of equations, of linear equations, and you try to determine the values for the unknowns in this system, and you had a system where you had more equations than unknowns.
Maybe it's inconsistent.
Exactly. Typically, whenever you have noise in there, when everything in the world is not perfect, you will end up in situations where simply two equations disagree. One says the value of x is whatever 1, the other says it's 1.1. So you may argue this is caused by measurement noise, by inconsistency, or the equations are simply wrong. And the approach we are addressing here is trying to find the solution that minimizes the squared error if I sum up the error of all equations. So just check what the value which best explains all my equations. I simply account for the fact that I can't make all of them fit, because with There's noise in the game. We're not living in a perfect world where all equations agree. So the goal is to minimize this error. And this is a standard approach which holds for a large set of problems. So every regression problem you treat typically, let's say you have a number of data points, you want to estimate a line, a straight line which goes through these data points. What you typically do is determine the parameters of the line, which are typically two parameters, x and b, or a and b, and so that the squared error, which is kind of the difference between the data points and the line, is minimized. It's really a standard approach. And the method has been developed in 1795 by Carl Gauss, actually when he was 18 years old, which I found quite remarkable. And he didn't even publish this work. He just developed it, told a few people about that, but didn't publish it the first time. Until 6 years later, someone used this technique to actually predict the future location of a newly discovered asteroid. It was in 1801. And the guy who used the ideas of Gauss to do that was the only one who was able to reliably predict where the asteroid will be in the future, because it was passing behind the sun, so it was unclear where it was going. And the person who used this technique was the only one who was able to actually predict where the asteroid would be. And this was kind of the first big showcase. And then actually other people published this method, and Newton himself, but he was actually the first one, or to be credited to him that he was the first one who invented this method. There are other publications in the beginning of 1800s, 1803, 1805, 1809, proposing this technique or very similar technique. Let's say we agree that it was Gauss who was the first one who actually developed these ideas. Okay. So let's go a little bit more into the details, actually tailored a little bit to the problems we are addressing here, that we have observations and we want to estimate the state of the system so that the observations we get, or the data we get, matches with our models, what we would predict. So giving a system of observation functions, let's call them Fi, and they map the state x into a predicted observation. So it's very, very similar to what we did in the column. Just given the state, what are we expected to observe? What's a predicted observation? Given that the rover is at a certain position and the landmarks are at certain positions, this is the state vector x, I can actually compute what I expect to observe if the world looks like what I have as my x vector, as my state vector at the moment. And then I also have a real measurement. This Zi. There's a real measurement I obtain, and I have the predicted measurement, the one that we had. And then, under the assumption that the observations we obtain, so these observations here, are noisy observations, we want to compute the state x, or x star, which best explains that. It's kind of, we have n different observations. We have potentially n different observation functions. If these are all the same type of observations, this function Fi may be the same for all observations. But if I may have different sensors or whatever different properties I want to model, these functions can be separate for the individual observations. And then as an input, I have this parameter x, and this influences the predicted observation, and I have my real observation. The goal is to actually find a configuration that the error between the predicted one and the really obtained one is minimized. And I'm going to look here into the square error. So just as an explanation, we have this variable x, which is our state, which is unknown, and this influences these predicted measurements. As we use our function f1 to fn, which uses the state and computes the predicted observations, so the variables that we had. And we have the real measurements, and we want to find an x so that the difference between those values is as small as possible. And we're looking here into the square differences. This is called least square. Okay, so one more concrete example. Let x be the position of 3D features in the environment that we can observe with the camera. And let zi be the coordinates of the 3D features projected on the camera images. kind of a projection from 3D to 2D. This is what we measure, the location of these features in my image. And then the goal could be estimate the 3D positions of those features in space so that the projection error is minimized. So that the projection the features generate are the projections that I actually measure, or are as close as possible to that. If you just have one single camera image, and you do that, and you find a solution, say, find a solution, what does it mean? Have you actually estimated the 3D locations of the features? This particular setup. So you have 3D coordinates. You have one single camera which observes those features. You have so in the camera, in the image plane, you have the projection from the 3D space onto the 2D space. And you now want to estimate, so you perform this approach, you want to estimate the positions of those features so that the distance between the projected point, I know that point if they are projected on the image, and what I measure where it is minimized. Say I find a configuration where all these errors are 0, which is the perfect case. What does it mean? Do I have correctly estimated the location of those features?
Projection doesn't represent all the information where you need. It can be, for instance, from the other side.
Exactly. So, where the issue that you typically have, you don't know if the object, for example, is 1 meter away or if it is 2 meters away, lying on the same ray. So, if you look where the light is going, the ray from the projection center through the image plane toward the features, the point can be somewhere on that line that will produce exactly the same reprojection, the same projection on the image. And therefore, this is, if you just have one single camera, this is not a solution. If you, for example, 2 cameras, like a stereo setup, you can actually estimate also the depth by using the information from both cameras. Just a small example how you can use this technique we are going to present in here in order to do state estimation. To estimate the configuration that best explains my data. Any questions about the, let's say, more general concept at the moment? Okay. So the key thing really is, we have these Fs, we have our real observations, Z. Based on F and the state, any state, we can compute the predicted observations. And so kind of we want to tune this X so that the squared error between those values here is minimized. That's kind of our goal. In order to do that, we need to define an error function. What would be the error function for this, for the first equation? F1 of x equals to that hat, and we have that. I'm going to compute the error between them. What's the easiest error function you can imagine? Exactly. The difference between them, to be interested in the squared error, we can square them. Exactly. And that's the way we do that. So the error E, so here if it's written in bold, this means that it's a vector or matrix, and if it's written non-bold, then it is a scalar, just to distinguish this, because we have the same variable E used twice, one bold, one unbold, but it should be pretty clear from the comments what we use. So we have the error E, this is a vector, which is just the difference between the observation we obtained and the predicted observation. And we assume, it's one assumption here, first all the observations are independent of each other, and this has a zero mean and is normally distributed. And then we assume that the error has an information in matrix omega, also very similar to what we did before. And then we define a squared error which takes into account this uncertainty, so the information matrix, as so this is volt E, the one here, is the difference between the states, times the information matrix times the value again. So if we set the information matrix to the identity, if the standard least squares formulation, so we just use the square error, we can kind of use the information matrix to, let's say, scale the error depending on how certain we are, for example, about the measurements. So if we are more certain about a measurement, it should count more in terms of errors compared to a measurement where we're very uncertain about the sensor itself. And this is what we call our error function. So the squared error, and this are the individual error terms. Okay. So this is the error for one single observation, therefore the index I over here. And if we have multiples of them, typically we add them up. So we can define the problem as finding the minimum of the function f, big F, where big F is the sum over the individual error terms. These are the scalar values we had before. And we are interested in the state x star, which is the best state, so the one which minimizes the error. We can also write this in this form, where we have here the vector form, so these are the vector terms, and the information matrix. It's all equivalent. It's the global error, so the individual squared error terms. So this makes actually an assumption that the observations are independent of each other. If I write that, we'll come to that later. And then this is just replacement by definition, by saying this is the definition of the individual scalar error terms. So now our goal is to actually find that x star. If I have that x star, I actually have a solution to my problem. If you now transport that towards SLAM, x in this case would be the location of the robot and the map, so the location of the features, for example. And then I want to kind of change my parameters, my x, my configuration, in a way so that the configuration I have is as best as possible in line with what I observe from reality. Any questions about that? It's very silent, which is not a very good sign. Is it too early for you directly after the holidays, or everything's okay?
This information matrix is really just for scaling the error.
Yeah, so what the information matrix does is it represents the certainty we have about our sensor. So the more certain we are, the bigger are the values in there. And if you consider how it is used in a Gaussian, so if you have a Gaussian normal distribution, we have something like some prefactor, and then we have x of 1 minus half x minus the mean transposed omega x minus the mean, right? This is how we use it in the Gaussian case. So this does nothing else, it's just scaling. So it's used in exactly the same way. It just scales the error, saying, about this error term we are more certain than about another term. Or this dimension of this error term we are more certain about than another one. So it may be that this information matrix measures some part of the state space very accurately, and some part doesn't provide me any information. Then the values in this information matrix will differ, for example, along the diagonal, also for the other values. If they're all the same, it's just the scale. So we have one measure sensor where this value is, let's say, the identity, and one where it's 2 times the identity. It just means that the sensor where we have 2 times the identity is provides the same information, but it's just more accurate. So kind of the same relation of importance of the individual dimensions. There was another question. Yeah.
So about the observation noise,
Yep.
we took to account here or not? And previously when we conducted the expected observation, or
The observation noise is all in here. Because we have an individual term for every measurement, so for the index I here. So it can be an individual information matrix for every sensor measurement. So for every sensor, or depending on the current accuracy of the sensor. Maybe that you observe something where the sensor has a very high certainty, or you have a situation where the sensor is very noisy, and you can have, although you use the same sensor, you can have that in the same framework. So another question. Okay. So, what's our goal? So our goal is to find this x star over here, and how do we minimize a function? Do we need to reduce the first derivative, set it to 0, we try to find the nulls. The problem is that this function may be arbitrarily ugly. So it may be quite difficult, especially in the nonlinear case, nonlinear functions in there, to find all the nulls. Or you have, let's say, sine, cosine functions, maybe have multiple nulls, all these ugly situations that may come up. So in general, it's very complex to actually compute this term. And there's no closed form solution. If you don't have any closed forms, we can try numerical approaches, which, or for example, iterative approaches, which try to get better at every point in time. And say I make also always small steps on my function, on the function I want to minimize toward the minimum, and then try to approach the minimum. So the Newton approach, for example, one way one could address that. Look to our, so an error function, we assume a certain shape, and then try to approach towards that minimum. And we'll do something very similar here. So, in general, there's no closed form solution, so we need to typically use approximations and iterative approach to come up with a solution. And what we typically do is make some assumptions. And one of the assumptions in here is that a good initial guess is available. So we roughly know these variables. So it's especially needed if you have an error function which has local minima. So if we have an error function which may look like this. For example, we want to find the minimum, so the global minimum in this case would be here. And if I just, let's say, follow the gradient of that function with my iterative approach, and my start value is somewhere over here, so this is the goal, or the kind of the true minimum, and can I follow this gradient, I will end up here. But I won't reach this one over here. So the assumption is, with this initial guess, that we are somewhere not too far away from this, from the true solution. So this is our initial guess is somewhere in that interval. It's not completely off. It's clearly an assumption, but for a lot of problems we can actually formulate the initial guess quite okay. As we said, if we want to estimate roughly, very roughly what the scene looks like, we may use our odometry information to easily compute a solution, start with this as the initial guess. In this context of slide. So for every problem, you have to come up with an initial guess on your own in order to approach the correct solution here. It may be that you, so depending on the shape of this error function, it may be that you don't need any initial guess, or the initial guess doesn't matter at all, then you're in a very lucky situation. But in most realistic situations, this is not the case. And the other thing we assume in here is that the error function is kind of smooth in the local neighborhood of the minimum, which is hopefully the global minimum, that we are right with the initial guess, but that it kind of has a well-defined gradient, it's not kind of some completely ugly function. Okay. If we do this, then we can apply an approach, which is often called iterative local linearizations, also called the Gauss-Newton approach, which we're going to present here, which is one way of approaching the solution. It works as follows. What we do is, since we have a potentially nonlinear function, error function, the first thing we do is we linearize it. Similar to kind of the hack, so to say, that the Kalman filter did, the extended Kalman filter did. If you encounter a nonlinear function, which you do not know how to handle in the Kalman filter, the easiest thing you can do is just linearize that function. That's exactly what we do here. So we linearize our error functions. So here the vectorized error functions around the current solution or the initial guess. So we need to know where we are approximately. And that's the reason why I need the initial guess, because I need to linearize at the linearization point. And that's where the initial guess is important. And then we follow a kind of standard approach. So you compute the first derivative of the squared error function, because that's the function we want to minimize. Then we set this first derivative to 0. As a result of that, we obtain a system of linear equations. It's a system of equations because with multi-dimensional problems, a lot of observations. And then we solve this linear system, and based on the solution of the linear system, I can obtain a new state estimate, so new x, which is hopefully closer to the global minimum. If the assumptions I made before are not justified, so a completely weird error function, completely far off, this may not be the case. I may approach another minimum, or I may even be far away from the minimum if my error function has a very, very weird, this is not a smooth function. And then we have last to reiterate this procedure. Why do I need to iterate this procedure? Why am I not done here after that?
Local minimum cases.
Yeah, but I mean, if you consider, let's say, back to the analysis course you probably had in school, if you want to estimate compute the minimum of a function, you with the first derivative, you set it to 0, and this gives you an indication where the nulls are. Why does it not work in this case? Why do we have to iterate this procedure and repeat it over and over again?
It's a linearized function of the real function.
Sorry. But so the reason is we linearize this function, but we only use an approximation. This approximation depends on our current state, on the initial guess. And so we kind of picture that's often easier. Let's say we are here in our function. If we linearize the error function somewhat over here, and I follow this towards, use the squared error, and then follow towards this gradient, that's all fine. If I have an error function which is completely weird, and I linearize somewhere, depending on where I am, I get a completely different gradient. And so if this function is kind of smooth, then the linearized function I obtain in this point is different from the linearized function I obtain in this point. And therefore, I have to make several steps and iterate this procedure.
We change in each iteration the initial guess.
So the initial so what we use in here is the initial guess is given once, and we always use the previous solution, the current solution we have. So you can see the initial guess as the current solution you start with, and then you always use the current solution. So the result of the new state is then used as the linearization point of the next iteration. Okay? Any questions about that? Okay, so then let's start with all these individual points and see how we can actually use this to come up with our solution. So the first thing we want to start with is the linearization. So we have to linearize our function, our error function E. And so it's kind of the bold one, so the vectorized form. What I want to do, I want to split this up into two terms. Not use x, but use x and delta x. And then x is the linearization point, and then the approximation of this function, I kind of vary delta x. This should indicate that delta x shouldn't be too big, it should be small. And if delta x is small, the approximation, the linearization I do is hopefully very similar to the original value. So I say, what this is equal to EI of x. Of x missing. Plus the Jacobian computed in the state x times delta x. And this is a standard way we use Jacobian as we used to in the common filter for linearizing our observation function, more for linearizing our prediction function. So just as a reminder, what's the Jacobian? Jacobian we've seen as the first derivative of a multidimensional function. So we have, and it's defined in this form. So this f1 over here on top, this is the first dimension of the function f, second dimension of the function until the mth dimension of the function. And this is x1, x2, xn, which are the individual dimensions of our input x. So what we need to do in order to perform this is we need to be able to compute the Jacobian of our function. Okay, so we have this linearization. We can now fix x, so our initial guess or our current solution, and then carry out the minimization in delta x. So delta x is the variable we're looking into. It's going to be the change in the state we want to compute. So what should be the change in our state delta x, which minimizes the overall error function? So I'm interested. So this kind of fixes the current initial guess, and I'm now changing these delta x. So how do I need to determine delta x so that it minimizes the error, the global error? Right? Okay. So how does this function look like? And that's actually something I would like to do on the blackboard, because it involves some derivations, and they're probably a little bit slower if you do it on the blackboard, but it probably gives you a better means for understanding that. And so this is not tailored yet towards SLAM, the standard least square approach, and it explains the individual steps ahead. So what do we have? We have our arrow function. I make this vector to indicate that here I is a vector of our state x, which was defined in which way?
Error is the difference between the predicted observation and
So it's the observation we obtained minus fi of x. The observed observation minus the predicted observation given the state. And then I had, this was the individual terms. We had ei of x, it was written as ei vector of x times the information matrix E transpose ei of x. And the function we wanted to minimize was the function big f of x, which is given as the sum over the individual error functions of x. Right? Okay. So the first thing we did to then minimize this function was to linearize our error function. So we have written ei of x plus delta x. It's just the information we had in the last slide. This was what? We approximate that. Our Taylor extension.
E of x plus Jacobian of x times
ei of x
delta x.
plus the Jacobian I. Well, yeah, of course it depends on x. Just call it. So this, of course, obviously depends also on x. So it depends on x. But I will drop the x, otherwise we'll get nuts with all the EDC. Okay. So this is our linearized error function. Now, let's see where this leads us to. If this is our linearized error function, the individual error function, the square error function is this term over here, so we have to take this term and replace the EIs with the approximated version. So EI of x, so this guy over here, is now is now approximatively, because I use linearization, ei of x plus ji delta x transposed the information matrix ei x plus ji delta x. Right? Looks good. Okay. What I can now do, can simply split this up into individual terms. And then I have ei of x transposed the information matrix ei of x. First term. What else do I get? Let's make it a little bit more interactive. All the individual steps are not too complicated.
People get transpose the information matrix
Yeah, so a little bit different. Delta x transposed, ji transposed. If I transpose, I have to change the order. The information matrix
and then error.
and ei of x. Okay? Continue.
Yeah. Maybe ei is. And
ei x. Information matrix
transpose that ei x again.
ji delta x plus, and now delta x transpose ji transpose omega ji delta x. Right? Good. Okay. And always note this is an approximation, so it's not an exact thing we do it. Okay, so now separate two of the terms. We have this term which stays the same, ei transposed. Just drop the x to save some space in here. Ei. And so okay, this was the first term, and now I seek to combine those two terms over here.
And the first one maybe you can combine.
The first one I can take exactly the same way, that's true. Delta x t j I t omega j I delta x. So, and then I have the two other terms which I can combine. How did I combine these two terms? Exactly. So the function here is a scalar. This is a scalar. That means all the individual terms are scalars as well. This is sum of scalars. It means these two terms are scalar values as well. So I can just take one, take this one, and transpose it. Because if I transpose a scalar, I don't change its values. Right? If I transpose this function over here, I end up having exactly this function. So this E becomes E transpose and goes first. The information matrix becomes the information matrix transpose, which is the same as the information matrix. And then these terms, they transpose them, they get swapped over here. So this is then 2 times this term. E I of x transpose omega I j I delta x. Right? So, is this step clear? I'm happy to explain it again if it's not clear why I can combine those two terms. Okay. So let's simply make some definitions now. So we are sick of writing all those terms. Let's simplify our life a little bit. Let's define this one as Ci. I call it Ci. I call it C because this term here is a constant in delta t. Delta t doesn't appear in here. Okay, so then I have this term over here, and I define this as the function hi. Just the Jacobian transpose, the information matrix index I, and the Jacobian. Let's call this a matrix I call H. And I use this term over here, and just say this is a vector VI transposed. It's just a definition of what I define. Okay. So, as a result of this, I can write this function as Ci plus 2 BIT delta x plus delta x transpose HI delta x. Right? What kind of function is that? I'm interested in this function as being a function of delta x. What kind of characteristic does this function have?
So linear.
Was it really linear?
No,
Quadratic.
Sorry?
It's quadratic.
It's a quadratic form. This is a quadratic term. This is a linear term, delta x. This is a constant. Quadratic form is just multidimensional quadratic function. So we have a term which is quadratic in x, we have a term which is linear in x, and we have a constant term. Okay, well that's good to know. We'll exploit that information. Next thing we do is we have defined the individual error terms. Let's see how big f looks like. So f of x. Now it's an approximation again because I use linearized information. It is the sum over I over the individual i's, ei. So I can just put exactly those values in. So I can write this as the sum Ci to Vi transpose delta x plus delta x transpose Hi delta x. Right?
Any normalization here?
Sorry?
Normalization, or to normalize the value of the f of x. So now,
Where should the normalization come in?
because we sum over this ei.
We sum over EIs, but why do you want to normalize that? That would mean that if I sum up the error and I would normalize this term, the error would always be 1, whatever configuration I put in. So we're not in the probabilistic world at the moment where we sum over all possible values we get with the associated with the probability, where we know that summing over the outcome of all the events is 1. This doesn't affect it. So there's no normalization or something like this. Okay, so I can continue by just rewriting this term a little bit. So moving the sum into the individual terms. I can write that as a sum over the Ci's plus 2 times the sum over Vi transpose times delta x plus delta x transpose the sum over the hi's delta x. Kind of clear? Just move the sum in there. And now I can actually use this to make a new definition. So I call this thing C, this thing B transposed, and this guy H. If I do that, I come up with the following form. So this is C plus 2 times dt plus delta x transposed H delta x. No, this is not transposed.
But delta x also for bt.
No, that was here. This is of course transposed. This was correct. It's just a delta x missing plus delta x transposed. Right? So again, this is a quadratic form. Okay. Now we have, so we linearized the individual scalar error and the scalar vectorized error terms. And we use the squared function, we square them, makes sense for linear function. I use a squared error, so they are a quadratic function. This also should be the case. This is an approximation, but I don't want to solve this approximation. So how do I determine the minimum of this function?
I derive it and set it to 0.
I derive it and set it to 0. Exactly. So you compute df, dx, plot this for this term. Okay, so I also need to cheat and look this up. In the linear case, it would be easy. It would be C would go away, and that was 2bt, and this would be kind of 2 times xt something. If you do this in matrix form, it's just a book. I also put it on the website, a matrix cookbook. Just look up to a couple pages and look for quadratic form, how to derive a quadratic form, and then the result for this derivation is then given by 2b plus 2h delta x. So this comes from the general quadratic form. So f is x t a x plus b t x. Then the df divided by x is a plus a transpose x plus b. Exactly. And so this is a general rule for doing this. And since our matrix A is symmetric, so a h plus h transpose gives 2h. This is why we have this term over here times x. And the factor 2 we had before, so the x go away. We keep this value untransposed. Just see matrix cookbook or any other linear algebra reference, or probably if monomerics, numeric if you want to look. Okay. So let's see where we are in terms of the slides. So in case you missed to write that down, that's not a problem at all. So we have all the derivation I did here on the blackboard is also written down here, so you can actually look that up and come to the quadratic form, and in the end we end up with this term over here where bt is defined like this and h defined like that. And this was exactly the same values we had here. So this form there is exactly the formula here. So next thing, as was said correctly, we need to derive that function, set it to 0. So we will have also the reference to the matrix cookbook, section 224. Here's a rule on how to do that. This is a general rule. If I have this function over here, I have h plus h transpose. Since in our case h is symmetric, this turns into 2h, and then I'm exactly there. So I can write that as the derivative of the function. So it is still an approximation because I approximated f and computed the exact derivative of the approximated function. Therefore, it's an approximate derivative of the original function. So this is exactly these terms. 2b plus 2h delta x. Okay, so now just follow what I do. I just compute the first derivative. Next thing I do, I set the first derivative to 0. So I say 0 should equal 2b plus 2h delta x. And this leads to a linear system. That's what I had before. I set the first derivative to 0. I end up here. And so what I do here, I divide by 2, minus b, then I end up having this term over here. So h delta x equals minus b. And then to compute the solution here, I have to multiply with h inverse on the left hand side. If I do this here, this cancels out. Only x survives, and I have minus h inverse times b. So I get my new updated delta star, the solution I want to have. And this is the increment I need to have. I need to add to my original state, or current state, in order to come closer to my solution. And then, as I said, I need to iterate this procedure because I used the linearization. This linearization is dependent on the linearization point. And therefore, these steps I do are only done assuming that I really have a quadratic error function. But my error functions are not quadratic in reality, so I need to relinearize at every point in time in order to get a better local approximation of my function. Okay, so just to summarize it, this is the so-called Gauss-Newton approach, or the solution, Gauss-Newton approach. I linearize around my current estimate x and compute for every measurement the error term. That was the linearization. So in practice, I really have to compute this Jacobian over here. And this Jacobian depends, obviously, on the type of measurement I have. Because I need to derive the observation function, and depending on the properties of my sensor, this results in the Jacobian. Then I need to compute the terms for the linear system, which is B transpose and H, or B and H. Just the definitions we did the derivations. So this is the error transpose times the information matrix times the Jacobian. And this is H, is the Jacobian transpose information matrix Jacobian. Therefore, I need the Jacobians to compute them because I need them here in these terms. Then I formulate my linear system. I solve the linear system, and then I update my state. So the new x for the next iteration is the old x plus delta x star. I iterate this procedure until this delta x is 0 or very close to 0. And then I'm there, hopefully, at my solution. Or at least I will be at the solution that this approach will find. Should we make a short break, or do you want to continue? Is a concrete example? Break?
No, I have a question.
Oh, of course, go ahead.
Is this guaranteed to terminate?
No. Because it simply depends how ugly your error function is.
Do you have threshold here to control the iteration number?
You typically, if you use this in practice, you have you limit that to a certain number of iterations you're going to execute.
And this calculation time, because too many Jacobians. Yes.
Sorry?
The calculation time, because we have a lot of Jacobian matrices.
The Jacobian matrix, so I mean, yeah, I mean, the complexity grows with the dimensionality of your problem. So computing the Jacobian just depends on how complicated your function is to evaluate that. But the complexity really grows with the state space. So the bigger the state space get, the longer the optimization will take. And it obviously also depends on the structure of the error function. Sometimes if your error functions are very, very well behaved, so can be very well approximated by a linear function, you convert it very quickly. If it's linear, convert it directly. And but if it's very, very ugly and has a very non-linear shape, then you may need more iterations.
So it's practical in indoor environment, instead of larger scale environment, mostly.
I don't get the question.
Because it should be practical in the small environment, not the really larger scale, because
I mean, the complexity grows with the state. I haven't told anything about how the complexity grows, how many iterations I need. The Kalman filter also grows with the dimensionality of the state space. So let's see how this evolves. Any further questions? Okay, so break or non-break? Break. Okay, 5 minutes break and we're going to continue. Okay, so let's continue here with a small example on how we can actually use the approach we derived here in order to come up with a practical approach or showcase where it's actually useful. So, and the idea here is odometry calibration. So it's pretty related to the exercise sheet you have. Your task is to actually realize what I'm explaining here now using Octave code. So assume you have a robot which computes its odometry by counting the revolution of the wheels, and this system typically has errors. So odometry is not perfect, otherwise it wouldn't be slammed. What we, however, would like to do is to actually eliminate the systematic errors of our odometry. Say, one wheel is bigger than another wheel. So whenever I drive, I always have kind of drift to the left or to the right hand side. And I can use calibration to actually calibrate those parameters and to come up with a so-called corrected odometry, which is not the perfect odometry information, but at least has no systematic error. And that's kind of the goal here. So we want to pre-correct our odometry to get rid of the systematic errors. And assume we don't have any information about how the robot works. So what is the driver of the robot? So we don't want to make any assumption on how the, let's say, modeling explicitly that it's the size of the wheels that may be different, or the air pressure in one of the wheels may be different. I don't want to go into the details. I just want to have a simple as possible solution to do odometry calibration in here. Okay, so assume we have some ground truth odometry information. Let's call it UI star. And this is available from some external source. So it may be that I put my robot into a motion capture studio where the robot is driving around at external motion capture equipment, which actually estimates the position of the robot very, very accurately. Another alternative could be a scan matching approach if I just want to use it locally, or I already have a scan system which works very well. Let's say I use the Kalman filter, a small size environment, works quite well, and I use this as kind of corrected odometry or ground truth odometry information. So I can actually run this mapping system to record a small data set, and based on this data set I want to compute the so-called calibration parameters so that I can then use the robot in any other context and I should get a bias-free odometry, so without systematic errors. It's kind of the key idea. So I have one data set, kind of a training data set, where I have the odometry information and I have the ground truth odometry information because I know how the robot moved. So what I want to do is I want to define a function which transforms the odometry UI into a corrected odometry, so that the difference between the corrected odometry and the ground truth odometry is as small as possible. And this is exactly the calibration problem I'm facing. So I don't want to make any assumptions how the robot is. Yes, of course.
The odometry error, is it mostly sensor measurement errors, or is it more slipping on the ground?
So it's more. So if you have typical errors, again, it's really not really sensor error, because what you have encoder disks which are connected to the wheels, and you have a sensor which measures the encoder disk. Even if you miss a tick at some point in time, typically these disks have a special code on there, that even if you miss one black-white transition, you can actually recover from that, because they have a special error correction code in there. So it's quite unlikely that the thing which counts the revolution of the wheels makes an error. It's more likely that you have slip. You're more likely that you have the wheel diameter doesn't fit perfectly. Depending on the payload you put on the robot, the air pressure, if you have air pressured wheels, is changed. The length of the axis of the wheels is not perfectly determined. Maybe you've unscrewed or rescrewed the wheel, changed the wheel. It's just off by 2-3 millimeters, not much. But if you accumulate these errors over longer periods of time, this can make a difference.
So then you have to recalibrate it every time you use the system?
Not every time, let's say you change your setup. Let's say. Or you can recalibrate this. Let's say you have tires which should use air pressure. Then you need to recalibrate it from time to time. Yeah.
So, for example, in this case, the robot that drives around campus, would you have to recalibrate it when you're sending it downtown?
Not really. So typically you calibrate that once. It's much better than what you had before. You may need to recalibrate it if you do a change in the system. So if you change the air pressure, if you change the configuration of the robot, let's say you attach a new sensor, it becomes more heavier, or you, let's say, unscrew the wheels, change something, put the wheels back. It's likely that you mount the things in a slightly different way, so that the parameters change a little bit, and then calibration helps. Any further questions? So it's a general comment. Whenever you have a well-calibrated system, your problems get much easier. So it's worth investing some time in calibrating things appropriately. Your estimation problems will get much easier in the end. But this is the general comment. Okay. So what we want to have is we want to have a function which maps the odometry we get into a corrected or pre-corrected odometry, and this function depends on some parameters. These parameters are x. Let's say we don't want to consider any internal information about where the wheels are located, how many wheels the robot has, what the length of the axis, modeling the errors in there. We make it better if we have that information and model that explicitly, but we say we don't want to have an approach that works basically for every system. We simply say, okay, we have a three-dimensional odometry information, for example. Our U, so let's say translate rotation, translation, rotation, or forward, sideward, rotate model, whatever we use. We say we transfer it through a function which is just a matrix of 9 entries, a 3x3 matrix, which should transform this raw odometry information into corrected odometry information, which gets rid of the systematic errors. And this is my design decision to say, I have these 9 values over here, which form a matrix, and this is exactly the function. I can put more background information in here and define a better function, no doubt about that, but that's kind of the easiest way to do that. So it's clear to everyone what this function f does. Okay, so what do we need to compute f in practice? All x1, x1, 2, 1, 1, 2, all these values over here. And to do that, we need this odometry and the perfect odometry. Okay, what's the state vector for this type of problem?
X, Y, Z, theta, the robots and landmarks we have.
No. state vector x consists of 9 different values. If I know these values, I know my function perfectly, and I'm all happy. Okay, what's the error function? How does the error function look like? It's kind of the ground truth odometry I have, and the corrected odometry. Should I take these two values into account? Yeah, and if I write this is true, this is u star I minus f, so my matrix is given by f of x times ui. So it looks like this. Right? Okay, so how does Jacobian of this function look like? We're not that trivial anymore. So what's the Jacobian of I? So I need to derive the first derivative of this function over here towards x, towards my state. So it's my, in this case, d e I dx. So I first, how would be Jacobi defined? Let's go back on the slides. Definition of the Jacobian. So here, the first row I have the first dimension of the function derived from the individual components of x, and then down here I have towards a different x. Okay, the function is the value of ui for the first dimension, let's call it x or whatever we call it, minus x11 times the first value of ui plus x12 times the second value of ui plus x3 times the third value of ui, right? So, and then this is the function, and then I need to derive that. df1 dx1 is, so the function is dx1 of this ui, or the first dimension x star minus x11 times uix plus x12 times uiy plus x13 times ui theta. Okay, so far?
And what does then this x1 mean? No,
This?
No, not this one.
This?
No. Yeah, this one.
To the first dimension of x. So the first dimension of f derives the first dimension of x. So the kind of, this is the first entry of the Jacobian.
But this is like x11, or is it a vector?
Yeah, so
x11,
it is.
x12, and x1.
No, it's not. It is x11, yes, you're right. Which is the first dimension of my x vector there. So that's, yeah.
U is our odometry information.
This is this value. It's a three-dimensional vector. It has, let's say, x, y, theta, or forward, side, rotate, or rotation 1, rotation 2, rotation 3, whatever I call it. Derive this function with respect to this guy over here.
Minus u or x.
Exactly. Just minus uix. Just only this term survives, plus the minus, because all these terms are independent of x11. This goes to all elements, just repeats for all entries. So what is left over is, so all values which are not shown here are zeros, so everything else is filled with zeros. The first element is just uix minus 4. It's exactly the value we told us. And so it's uiy, ui theta for the second one, and the same thing repeats over here. So this derivative is a special form. Something is really, sorry,
No.
go ahead.
So identity matrix.
This is not an identity matrix, not at all. How many dimensions does this matrix have?
Three by 9.
9
Yeah.
columns and 3 rows, yes. So identities are to obtain. So of course these values are 0, but that's not what I want to point out, want to point you out through. What's the important thing about this Jacobian? Why is this a very, very easy and very nice form for us? So we have a function that depends on x. We derive it. And this function, does it depend on x? No. It doesn't depend on x, it's great. That means the whole thing we have is linear. It's a completely linear problem. So if the Jacobian does not depend on the linearization point x, it's the same everywhere. And that means we have a linear function. That means we have a really quadratic, so the scalar error function is a really quadratic form. It's not an approximation. So it doesn't depend on x. What does this impose? The scalar error function is really a non-approximated quadratic form.
We only have to do one iteration.
Exactly. We don't need to iterate because we directly approach the correct solution. So E is linear. So this is the Bose E. So the vector form is a linear function in x. So there's no need to iterate for us. Directly executed, one shot, we have the solution. We know our parameters, and we're happy. There are questions about that. Okay, and I have a few questions. How would the parameters look like if the odometry is already perfect? Exactly, the parameters, the function f would be an identity matrix. So x11 is 1, x22 is 1, x33 is 1, and all other values are 0. Okay. So how many measurements, odometry measurements, do I actually need, at least, in order to come up with a solution here, with a valid solution? Sorry? 9, you're on it's the correct idea, but wrongly implemented in your brain, so to say. So the idea is absolutely right. I have 9 unknowns, but every odometry information you need has 3 dimensions. So I need at least 3 odometry measurements, because then I can generate 3 equations per measurement, and I can generate 9 equations of 9 unknowns. So it's the minimum amount of odometry measurement that I need in order to calibrate that. Of course, it's much better if I have more. Hey, H is symmetric, that's what I told you. Y is symmetric. In general, for these kind of problems. How was H defined? sum over product of three matrices. Yeah. Just as a transpose. That was the definition of H. What about this matrix? No, not necessarily. And in this example, no. But it's symmetric because information matrices are always symmetric. So I have here a matrix transpose times a symmetric matrix times this original the matrix J again. So the product of these two matrices transposed and untransposed, which always ends up in a symmetric matrix if the matrix in the multiplication here is symmetric. So all of these guys are symmetric. And if I add a couple of symmetric matrices, I end up with a symmetric matrix as well. Okay, that's the reason why it is important. H is symmetric. How does the structure of my measurement function in general impact or affects the structure of H? Probably the most tricky question here. It's pretty related to the Kalman filter, where we have a measurement function which measures only a subset of the variables, or the visibility range of the scan. We have a similar effect here. What happens if my observation function only observes a subset of the variables? So if I can't observe a large part of the state space, I can only observe one variable.
Uncertainty about the rest of them is still very big.
I'm not talking about any uncertainty here at the moment. If I measure only one dimension, the error for the other dimension is 0 because I don't measure anything. If the error only affects one dimension, means that the Jacobian of that guy is 0 for all other dimensions as well. Right? If I can't observe anything, doesn't contribute to any error, the derivative is 0. Since H has this structure over here, if these J's are 0 in basically all dimensions, except of a single dimension, perhaps, the matrix I generate in here is super sparse. This has very, very little entries. So the number of state variables I can observe at the same time impacts how dense this matrix H will be. And the sparser this matrix H will be, the easier, as we'll show later on, it is to solve a linear system. So therefore, there's a practical implication. If I have a matrix that is very, very sparse, I can solve a linear system very efficiently. So how do I do that? How do I solve a linear system? How to do that in an effective way? So the linear system, H delta x is minus b, and I want to solve that. Of course, the standard approaches are really invert H, and multiply H from the sides. I compute H minus 1, and then compute minus H inverse times b. But that's very, very ineffective. At least the cubic complexity. Or at least the cubic complexity. So better solutions to that are things like geometric factorization, periodic composition, or other iterative methods to compute the inverse. And actually, if you use the backslash operator in MATLAB or in Octave, to do that, it actually will determine one pretty good solution to the heuristic that solves this for you in an efficient way. I just want to very quickly illustrate how Cholesky decomposition can be used to do that in a more effective way. So, assume we have a matrix A which is symmetric and positive definite, and we want to solve the system AX equals B. In theory, what I would need to do, and we would need to invert AA and multiply. So inverting A is very costly. So a better way to do that is to compute the Cholesky decomposition, which leads to a matrix L transposed, which is equal to A. And the properties is that this L is a lower triangular matrix. So half of this matrix is 0. Okay, what I can do then is I can first solve the equation Ly equals B towards y. So that I have that y equals L to the power of minus 1b. And then solve L transpose x equals y. Just by replacing that, I get that. If I do that, since L is a lower triangular matrix, it's very easy to do that. Because if it's a lower triangular matrix, you can just do one step in the Gauss elimination, and you have the solution. So you start with the element where you just have one entry in the matrix, you know this dimension. Then you put it to the next line, you eliminate this line, just one variable is left, you get the second variable, and so on. So just need one path through the matrix in order to compute that. And therefore, Cholesky decomposition is one of the effective means to solve that. Okay, so the Gauss-Newton approach in sum, what have we done? It's a method to minimize the squared error. We typically start with an initial guess, so we need some information unless we have a really linear error function, or quadratic scalar error function, linear individual error terms. We need to have an initial guess, which shouldn't be too far away from our solution. We linearize individual error functions, so the vector terms. This leads then to a quadratic form. We compute the first derivative of the quadratic form, we set it to 0, we solve it, and this leads to a state update, or S state update, and then iterate this procedure. It's kind of the standard way to solve that. There are potentially better ways to do that, more effective ways to do that, assuming errors in different error models in your observation functions, but that's kind of the standard way to do that. And what we're going to look into next time is how can we actually exploit that framework to address the slam problem. But before that, I would like to give a very, very brief sketch on the relation between this technique here and probability theory. Because so far we said everything should be done probabilistically, we have our models and we do state estimation, and everything was done using probability theory. So far I haven't really talked about probabilities here at all. I just introduced this information matrix rather magically and said, here we go, here's the solution. And so the question is, how does the solution I present here relate to state estimation in a probabilistic sense? And we can actually show that the solution one finds here is the maximum likelihood solution if every distribution is Gaussian. And this can be quite easily sketched, so you can go in much more detail just a sketching here. So in general state estimation problem, we want to estimate x0 to xt given our observations and our commands. And just by applying Bayes' rule, the independence assumptions between measurements, the Markov assumptions, I can actually formulate it in exactly this way. It's a normalization constant times my prior information about x0, and then a product over the motion model in the Bayes filter and the observation model. It's kind of standard way to do that. So it's just applying Bayes' rule, independence assumption, and Markov assumption, as we've done that for quite a couple of times in this course. So this is exactly the same with this term, under the assumption, the independence assumption, and Markov assumptions we have done. Okay, so now let's not consider the probability, let's consider the log likelihood, so the log of that term. So just compute the log of that term. If I compute the log, the product turns into a sum. The first term, which was the normalization constant, is a constant, so it's still a constant if I take the logarithm. I have the logarithm of this prior, and I have the product, and the terms in here are logarithm, and I have the sum over here. Okay, now let's assume we have Gaussian distributions. Everything is a Gaussian. So we say this guy is a Gaussian, this guy is a Gaussian, and this guy over here is a Gaussian distribution. Then we have to need to look into what means if I take the log of a Gaussian. So if I have the Gaussian distribution, what I evaluate x, the parameters mu and sigma. This is actually a constant, so the factor, and then it's just the exponent is left. So minus 0.5, x minus mu transpose, sigma, x minus the mean. Just applying the law. If you look at these terms here very carefully, say, this is very similar to my arrow function. So these guys over here, you can say, this is just my arrow function, my vectorized arrow function. The inverse of the covariance matrix is my information matrix. And this is the non-transposed term over here. So this whole term over here is exactly my terms E of x, my scalar arrow values. So up to a constant, still have that constant in here, but up to a constant, and this constant only depends on the information, on the covariance matrix. I can actually, this term is equivalent to the individual arrow functions. That means I can rewrite my Gaussian as another constant, which takes into account the constant before and all the constant accumulated on the way. The arrow function, which is relevant for the prior, plus the arrow function from the odometry information and the observation. And that's nice. Because what I now have is a sum of arrow functions, which I had before. And the only thing I have is a constant in here. Okay, but the nice thing is, what I do if I try to maximize the log likelihood. So if I maximize the log likelihood, I also maximize the probability of the value, because the log is a monotonic function. And if I do the maximization, I don't care about the constant. So maximizing this function, the argmax of the log of these probabilities, is equivalent to the minimization of the negative term, and I can ignore all the constants. So I end up with this value over here, this value, this value. And this is exactly the form that I have in my arrow minimization. So minimizing the squared error is equivalent to maximizing the log likelihood in terms of Gaussian distributions where the individual error terms are independent of each other. So if I do this Gauss-Newton approach to find the solution in the error minimization sense, what I do, I actually find the mean if everything is a Gaussian distribution. And therefore we have a strong coupling between this squared error minimization and the probability theory. So I do exactly the same assumptions I did before, and I can actually, with this trick or with this equivalence, I can actually show that minimizing the squared error is equivalent to maximizing the log likelihood. Okay, so to summarize that, what have we done today? I introduced the problem of least square error minimization. I presented one technique, which is the Gauss-Newton approach, on how to address that problem, especially for nonlinear functions. Therefore, need to linearize and need to iterate. The approach makes use of linearizations, and therefore this approach is definitely an approximation, unless I already have a linear function. And it is equivalent to finding the mode or the mean of our distribution if everything is a Gaussian. And this is actually a very, very popular technique you find in a lot of disciplines. So not only computer science, in really a large set of disciplines where you do need to do regression, where you want to estimate any model parameters given some observations you have. This technique is one of the standard choices which are used. Okay, so that's it from my side. Some literature about least squares and Gauss-Newton in general. You can basically take every textbook on numeric calculus or on optimization, and one of the first chapters will actually show that, what we have done here. Also, Wikipedia has a quite brief and not too bad overview about that, and kind of the key derivation and some hints to further literature you can also find on Wikipedia. And if you want to look into the relation between the error minimization and probability theory, you can also look into the progressive robotics book. There's one chapter, one subsection which shows the equivalency and the derivation, but it mainly uses the steps I presented on this one. Okay, are there any questions from your side? Okay, so then thank you very much. We're going to use this framework next week to address the SLAM problem. So this was kind of the general framework today, and next week we say, how does it look in practice if I want to use it to address the SLAM problem? Kind of, how does this matrix B look like? How does H look like? What kind of special forms do we get or special properties do we have in the context of the SLAM problem? And how can we actually solve such a problem in an effective way? Okay, that's it from my side. Thank you very much, and see you next week.